Hello and welcome to all of you. We are very pleased to be back with this webinar series which seeks to empower your full workflow of baseplate and anchor design in collaboration with one of our key partners, Idea Statica. The running webinar series have three chapters. The first chapter already concluded in April 2025, where we presented Idea Statica chatbot as the solution to simplify your structural data exchange process. In the second chapter, we introduced the new Hilti innovation, Smart Design, which seeks to reduce the number of iterations to find the best suited anchor system. Please send us a message here in the chat if you wish to see the recording of those webinars. And today, we will complete this webinar series focusing on baseplate design with CBFEM engine at its core. And let me give you a bit more details about the agenda for today. We will start with the challenges faced by the structural engineers today with interrupted workflow of baseplate design. Then we will take you through the details of the design code, rigid baseplate assumption, and we will deep dive into component-based finite element analysis. And we'll end this session with some real-life examples and the best practices. But before we get started, let me introduce the presenters for today's webinar. I have with me Stefano Kusuma Ali, product engineer from Idea Statica, who will later formally introduce himself and Idea Statica. And I am Kaushal Agrawal, the regional software manager, looking after our structural software solutions, where PROFIS Engineering is one of the major solutions for structural connections. Just for the benefit of the participants who might have not been introduced to Hilti before, Hilti was founded in 1941 in Schaan, Liechtenstein. We are a global leader in system solutions for construction professionals, and we operate in 120 countries, have 34,000 employees worldwide. Our purpose is making construction better, which we want to achieve by being our customers' best partner for productivity, safety, and sustainability. We want to create value through leadership built on differentiation with our drive and investment in innovation and our direct customer relationship, which is our unique model that helps us to make you understand and your needs to bring you the best of the solutions. And in this webinar, we will be taking some of these intriguing questions such as, is your baseplate rigid enough to comply with the applicable codes and have a safer design? How do you calculate it? Questions such as, how can you be more productive, streamlining the workflow of overall steel to concrete connections? And how can you optimize to be more sustainable? Being able to produce safer, more productive, and sustainable designs are some of the building blocks of spec to site solutions. Let me give you a bit more context about spec to site solutions. As a structural engineer, there is a need for making cost effective, more sustainable, and reliable designs of structures. It is also important to optimize the structural connection design process. Once the design is ready, the engineer wants to be sure that the design is installed as specified. We at Hilti address all these needs with our spec to site solutions. These solutions deliver value in several ways, including hardware solutions, design methods, software, training, engineering center, installation approach, and being available on job site. Let's watch a small clip to understand a bit more about it. So, what you saw that Hilti wants to partner with you to value engineer higher performing specifications that give more peace of mind and are more sustainable. We want to help you improve key elements in structural connection design to be the best partner for productivity, safety, and sustainability. We do this by offering our spec to site solutions. Now, it's time that I hand over to Stefano, who will now introduce himself along with the Idea Statica. So, Stefano, would you be sharing your own screen?
Thanks, Kaushal, for the introduction. So, my name is Stefano Kusumali. I'm a product engineer in Idea Statica APEC. My background is structural engineering with about 5 years of working experience. So now I'm going to introduce about our software Idea Statica. So Idea Statica is a world-leading software for analysis and design of steel connections and concrete details. So as you can see, we are more focused on the detail instead of the global 3D model. So with Idea Statica, engineers can do safe and fast design, code check anything, design any geometry, any loading in minutes, then deliver projects without compromises. Idea Statica has these two main branch of applications. One is steel and another one is concrete. So for steel, you can design connection with any geometry. You can also do anchoring and footing design. You can also do frame design. In concrete, you can actually model and design wall, cross section, and also beam with discontinuity. Now we also have this one special application which is called Idea Statica Checkbot. Why do I mention Checkbot here? Because with Checkbot you can actually connect FEA CAD software with the Checkbot, and then you can export it to our Idea Statica connection, or you can use it to export it to Hilti PROFIS. Right, so let's jump to our next topic: codes, calculation assumptions, and main challenges. So basically, we identify three main challenges that structural engineers face while designing steel to concrete connections. Firstly is the interrupted workflow, because we are using many different softwares and how to transfer the data between them. Next is a rigid baseplate myth. How can we confirm that our baseplate is actually rigid? Last one is CBFEM. I will be explaining about how CBFEM work and of course the assumption and methods behind it. Right, so the first topic is interrupted workflow. Basically, as a structural engineers in our field, we have a lot of different softwares and tools that we use. Right, the question is how can we transfer data between them without any error, right? Because an error would be quite dangerous for us structural engineers. And yeah, normally people will be using Excel and all that, but here we have a solution, a better solution for you, which is called Idea Statica Checkbot. So as I mentioned in the beginning, Idea Statica Checkbot can be integrated with a popular FEA or CAD software. So let's say you are coming from an FEA software. So data that is transferred from your FEA to Idea Statica Checkbot would include the geometry of your structure, the cross sections, the material, and of course the internal forces of your structure. So Idea Statica Checkbot will act as a data hub for your structure engineering data. And after that, you can export it seamlessly to PROFIS Engineering. So this workflow actually solves the interrupted workflow challenge, and now it doesn't require you to do manual data transfer anymore.
Thanks, Stefano. And let me give you a bit more detail about the survey that Hilti conducted with more than 1,300 users to understand the estimated time it takes to complete a full design. From designing using structural software to designing the connection and finally exporting to BIM and CAD software. When we accumulated the survey results, we found a significant amount of time saving can be made using PROFIS Engineering integrated workflow. We will now focus on the connection components design, and you will see how easy it is with one click from anchor to base plate to welds. So essentially, PROFIS acts as an intermediary between all design software, speeding up the workflow and reducing the likelihood of manual errors. And that actually brings us to the first poll of this webinar. And here we would like to ask you, do you also face similar issue of using multiple design software for baseplate designs? And here I'll give you the poll, and we'll wait for a few more seconds before jumping on to the next part of the webinar. Okay, so now we are at the core of this webinar where we are going to talk about the design codes and the rigid baseplate assumption. And here we would like to start our discussion with one of our innovative anchors, HST4, which offer higher tensile capacity, design flexibility, thanks to variable amendment depths and approvals that meets a wide variety of application needs. Also, softer feature like rigidity check and the CBFA model and overall joint design can help in making your applications higher performing and can be optimized further. And then the next question comes is that what are the components in this steel to connection that must be designed? So these are profile, welds, base plate, stiffeners, anchors, and the concrete check. And traditional anchor software offers solutions for only a portion of this connection. However, PROFIS Engineering provides solution for the entire steel to concrete connection. And throughout this webinar, we will see how to design the base plates, the welds, the stiffeners in a more productive manner, which will help you to produce more successful value engineered specifications. Next, we are going to look at closely at the standards and the codes that define a connection between the anchor design and the base plate. And let us take a closer look at the code and what it states. And specifically, we are talking about here the Eurocode. And I would like to draw your attention towards section 6.2.1. And the experts of the code has been taken here for your reference. And let me read out for you. So it states simply that the tension loads acting on the anchor to be need to consider baseplate rigidity. In fact, the designer must confirm the baseplate remains elastic under design actions and deformations remains negligible. And if this is not confirmed, then deformations on the fixture need to be considered in determination of tension loads acting on the fastener. Now, this is a very critical assumption that must be validated. In other words, designer needs to check baseplate rigidity, and if that determine the base plate is not complying to the rigid base plate assumption, then you are outside of the EC2 part 4 guideline. And that's the base plate rigidity myth that we wanted to point it out. And here again, uh, it raises some questions, which is how to confirm base plate rigidity. And it is not an easy question to answer that we discussed just now in the previous slide. And many designers are not familiar with the rigid baseplate assumption of EC2 Part 4 that a baseplate must be sufficiently stiff. And hence in practice, this means that this basic assumption is often not considered. We again emphasize on the fact that we understand the rigid baseplates is a theoretical approach, and using that, the design process gets simplified. But in reality, plates deform, and there are many factors which are highlighted over here that influence the load distribution on anchors. Let's understand this in a bit more detail. First, we bring the example here of the tension loading. And on the left hand side, what you see is the rigid idealization of a rigid base plate. And on the left hand side is more of a flexible base plate. What you see here is that the rigid base plate shows no deformation. The tension load is distributed evenly on the anchors. But for the flexible base plate, the prying effects are visible, and the respective prying forces add up to the anchor tension load and must be absorbed by the anchors. Next, what we have is the case where the moment is being applied. So here at the top, you can see that we have the idealization of the rigid base plate, and on the bottom, you can see the flexible base plate. And here, if we try to put it mathematically, what you see here is the center of tension and the center of compression, basically. And to satisfy the equilibrium of moments, which is external moment equals to the internal moment. The internal moment calculations need to happen with this load multiplied by the lever arm. And here, in the case of rigid, you get the full lever arm because the center of compression actually lies somewhere here. But if this base plate is more or less flexible, then the center of compression shifts from this location to somewhere around this location, and hence the lever arm gets shortened. As a result, uh, the and to satisfy the equilibrium, the loads in the anchors have to be increased so that the equilibrium condition can be satisfied. Right, so moving on to the next part. Okay, so this is just a depiction of what we were discussing. Here you can see the 10 kilonewton load is applied, and that's actually divided equally into the anchors in case of rigid, but in case of non-rigid base plates, this can, depending upon how much flexible the base plate is, this can go to even increase up to 6 or 7, or it depends upon basically the flexibility of your base plates. So what we want to conclude here is that the base plates are actually thin elements and they bend and deform. And ignoring base plate bending can result into underestimation of anchor forces. And hence the assumption on rigidity must be verified by the designer. And remember, anchor resistance design requires rigid base plates. Now, as we discussed, I would like to point out here that, can you actually determine by looking at these pictures that which of these base plates are actually rigid and which are not? And as I pointed out earlier, it's not a very easy question to answer. Why? Because uh, if you look at some of the documents that try to address this topic, we find several definitions. And here I'm pointing out to the four definitions. So one of the definitions says that the distance between the profile surface and the base plate edge um, should be limited to 4 times the thickness of the base plate. There is a requirement from EC2 Part 4, of course, that the deformation of base plate, which is in this case deformation of the base plate, should be negligible in comparison to the anchor displacement. Okay. Then we have one more requirement or one more suggestion, I would say, that the stresses should be lesser than the yield stresses. And there is one more theory which says that the placement of the anchors should not be too far away from the baseplate edges to avoid prying forces. But at the end of the day, what we like to point it out here is that there is no generic answer to the question of the sufficiently rigid. And what we want to say is that every case is a standalone case and should be verified independently. To help you solve this challenge, PROFIS Engineering provides side-by-side numerical and graphical evidence of a assumed rigid base plate compared to the non-linear real-life results. So what you see here on the slide is basically on the left you have the equivalent rigid base plate, and on the right you have the component-based finite element method base plate. The software calculates the deviation of the actions on anchor between the modeled base plate and an ideally rigid base plate as a percentage. The greater the percentage deviation, the less the code compliant the modeled base plate is. You can then decide for yourself what extent the base plate is sufficiently rigid or whether the further adjustments to the design are necessary. And here we can have a look at one of the examples where you can see uh, that when compared to the rigid base plate on the um, realistic conditions, the anchor forces have an increment of about 50% and deviating about 50% in tension. In other words, the flexible base plate in this case is generating significant prying tension forces on the anchors. And the question remains, would you consider this as rigid or sufficiently stiff or flexible? Um, and that brings us to the second poll of this webinar, where we would like to ask you, do you also consider your base plate to behave as rigid? And let me launch the poll for you. Here's your poll. And I'm going to give you a few more seconds to answer this for us.
Alright, thanks Kaushal. So let's jump to our last topic, which is CBFEM and black box filling. Right, so in this part, I will be explaining how CBFEM work and of course the assumption and methods behind it, because I understand as a structural engineers, you would want to understand how the analysis actually works and you want to make sure that everything is working correctly and safe. Right, so CPFAM is actually a synergy of component method and finite element analysis. So as you can see, it's a component method with synergy of finite element. Inside CPFAM, your model will be separated into several components. Number one will be plate, which is including the members like this I members here. And then second one will be weld, bolt or anchor, and the last one will be concrete. Then after the CBFM analysis is run, the forces of each element will be checked against the code equation. So for the first component, we have steel plates and members here. Basically, all the steel plates and members will be modeled as shell elements, as you can see here, and they will have a non-linear material model with it. After the analysis is run, you will get the result, you will get the strain, and these shell elements will be checked against the strain. And we're using the strain limit of 5%. Next, we have weld and anchors element models. For the welds, is basically it will also be transformed into an equivalent weld shell element and then connected to other shell elements using multi-point constraint. Once the analysis is finished, we will code check weld against its stresses, basically. And next we have anchors, which will be modeled as a non-linear spring inside the analysis. And once the analysis is run, we will get the anchor forces, and then we will co-check it against that forces. Last one, we have a concrete block model. Basically, the concrete will be modeled with a compression spring which has a wrinkler subsoil model. And after the analysis is run, you can check the contact stresses from the base plate and concrete. And prime force is also included in the our plate model and also in the force of the anchor bolt because we are using finite element analysis, as you know. Right, so what are the key steps of using CBFEM? Basically, if you are using checkbot, you'll be importing the geometry, cross-section, and the loads automatically. You'll have the model, then once you click calculate or click run, then the analysis model will be created automatically for each component. So you don't need to specify the mesh and all that. It will be created automatically. Then the third step will be analysis already performed. So as you can see here, this is your model. Then the analysis model will be created automatically here. And lastly, the analysis is already performed. Because of the CBFEM which is implemented behind the software, you can basically model any typology, any loading, and analyze it within minutes. So as you can see here, finish your analysis, then basically all your elements such as anchor, weld, stiffener, concrete, and so on will be checked against the design code. So basically our analysis is fully code compliant, and as I mentioned before, the plate will be code checked against the strain, the weld will be code checked against its stress, and the anchor will be code checked against its forces. Right, so basically your analysis is fully code compliant. Right, so just to reiterate, basically you can model any geometry and any loading, right? And then the FEA model will be created automatically by the software. You don't need to specify the meshes and all that. Then you just need to review the result once the analysis is finished. We also understand as a structural engineers you would want to understand how CBFEM works in detail because you would want to make sure that the structural analysis and design that you do is safe, right? So for those who would like to understand more, there is this book by Professor Walt which describes in detail his research finding and the methodology. Next, we also do a lot of verifications with several universities for many years, and of course, it's still ongoing, which includes live testing of steel to concrete joints. Oftentimes, we also compare the result from our software with other finite element analysis software. So this is done to ensure that our analysis model is safe and accurate.
Okay, so S- Stefano talked about all components of the base plate or steel to concrete connection except maybe anchors. So let's me give more details about how do we idealize anchor in the FEM modeling. So we do this by modeling them as non-linear tension-only springs, and here the stiffness of these springs actually comes directly from the experimental Hilti research for the product assessments. And the I would like to point it out here that the anchor stiffness is a product specific characteristic. Why? Because here on the right hand side you can see that there is a graph which shows that the relationship between the force applied and the displacements in the anchors, and you can see that some of these anchors can be mm, termed as stiff anchors because uh, they form much lesser in comparison to the softer anchors. And to emphasize a bit more on this concept, let me bring in the the comparison here of two different cases. So let's say first of all we are dealing with only tension cases, and here you can see is that the stiffer anchoring system tries to, of course, not deform at its location, but the tension load which is applied with the profile try to bend the base plate at the center, and hence producing more prying effects in comparison to the software system, which actually deform along with the base plate, and hence the base plate remains more flattish in comparison to the stiffer anchoring system. So in this case, basically you can say that the software system can perform much better in reducing the prying effects, and hence uh, the anchor increase in the anchor loads. On the other hand, we have another case which is compression and the bending, and here you can see is that uh, the stiffer anchoring system performs better in terms of that it allows the center of compression to remain at its own or closer to its own location, because this anchor system actually doesn't deform a lot. While in the cases of the software anchoring system, they deform, and hence, the center of compression shifts more in comparison to the stiffer system, and produce more prying effects in case of software anchoring system. So in conclusion, what it does is that it also drives the discussion of which anchor should be selected for which case. So this based on the loading, we can suggest the softer and the stiffer anchoring system. Uh, what it also tells that doing the FEM analysis for one anchor is not equivalent anyway with any other anchor, because the two anchor system can perform way differently from each other. And with this, we are at the point where we should move towards the PROFIS engineering and show you the real life example. So here what we are going to show you is that how you can utilize your free standard version to do the rigidity check. In case you have designed your base plate outside of PROFIS engineering and you just want to check whether the designed base plate is behaving rigid or sufficiently rigid or not, that is something you can check with your free standard version. But just in case if you want to design the full base plate and all its components, then what you would need is the paid and the premium version. So let me switch to my PROFIS engineering. Let me see if I can do that. Yeah, okay, perfect. So here I am, and there is an example that I like to show. So let me start with this, and let me switch off my camera here so that you can see my full screen as well. Perfect. So what I can demonstrate from here is that there is already a base plate size selected, which is 300 by 460. There is a profile here. There are four anchors, and we can dive into the case. There is a concrete grade selected. The geometry of the base material is decided. So everything is here is perfectly selected. And what you can see is that the anchor system right now is passing with the maximum utilization up to around 79% in concrete breakout, which is a good case. I mean, so this anchoring system is perfectly okay in case when we are doing the rigid design. But as a standard user, as I said, I'm using the standard version for now, and I can still do the anchor plate rigidity check. So I can do this. So let me switch it to the check, and then let's calculate. So here I can see is that, okay, I have 27% difference coming for anchor number one and anchor number three. Because of the heavy moment that I have in the MY direction, which is of 898 kilonewton meter. If I confirm, then basically the software designs the anchoring system based on the new loads. And in this case, it's failing in bond by 109%. So this is the case where uh, you have decided your base plate size, your base plate thickness outside of the scope of PROFIS engineering, or it is pre-decided or pre-attached, and you just want to check whether the selected base plate size and this and the thickness is sufficiently stiff or not. In this case, it does not look like that it satisfies the criteria. So what we are going to do, we are going to go back to the home page and switch our version from the standard version to the premium version, and it's gonna refresh, and we are going to open the same example that we were working earlier. So let me open it, and now we are in full-fledged premium version. In here, again, I'm going to check with CBFEM that what is the difference between the anchor forces. So I have the similar results as I was having in the standard version, that there is a 27% difference in the anchor forces. Now there can be two approaches which I can take from here, because if I confirm this for now, again, my anchors are failing in bond by 109%. It's a similar result which we had in the standard version. So one is that I can make my uh, base plate thicker, so I can make it, let's say, 24 mm instead of 18 mm, and click on calculate. And here you can see that the difference, which was 27% earlier, is now just 10%, and I can confirm, and now my anchor system is passing by the utilization of 97% as the maximum. Now, which is good. And the anchor plate check is happening, and also the concrete check and the profile checks are happening, which is good. But now let's say for whatever reasons I do not want to increase the thickness of the base plate and I want to still have the 18 mm base plates, then what would be the solution? So maybe I want to look at the stiffeners. So here I will go towards stiffeners and going to use the stiffeners, because this is a moment case. I'm going to use stiffeners towards the center of the flange at both the sides. So here you can see that, and I'm going to use the chamfered plates for this, and the thickness I'm going to use is 16 mm, and the length that I'm going to use is 80 mm. Now this looks good, and let's check it with the calculation button. So now here you see that the difference, which was 27% earlier, has been drop down to just 7%. If I confirm, I can see that my anchor is still passing with 93% utilization ratio. The anchor plate is at 100%. The stiffeners at 92%, and the concrete and the profile, everything is passing. Now in this case, the weld which we are using is full penetration weld. So instead, if I have the fillet weld, then I would need to change them to fillet weld here quickly, and I'm going to use 6 mm weld for this case, and let's run more analysis. So here now you can see that it has increased a bit because of the loads being transferred through the weld, and if I confirm, I'm still completely passing the design and the checks, and the weld utilization at 99%. So this is all good. And from here, I can create the report. I can take it to produce the drawings from here using the 3D model export functionality. I'll just quickly share that's what's you will gonna get in the report. So let me just open it. So here you can see first of all the input um, that we have given. Then the anchor calculation has been presented. And then in the section number 2, that is where you can see the anchor plate and the base plate design has been performed. And you can see that from where we have picked up the stresses values and comparing it against the yield stress, the yield strength, basically hole bearing check, and the weld check, um, mm, the weld which is connecting to anchor plate to profile, and the stiffeners to profile in the anchor plate, and then the concrete check. Um, and then at the end of the day, the fastening meets the design criteria with all the maximum utilization 100 or below 100. Right, so now this is the example which I wanted to show. So even if you have basically in conclusion uh, the um, standard version or the premium version, the major difference is basically if you have already have your base plate size and the thickness fixed and you just want to check whether that's stiff enough, then you can still utilize your standard free version to do the rigidity check and design the anchors for the elevated loads, if any. But in case of premium, you can do the full base plate design along with the stiffeners, welds, etc. And now it's a time that I like to play a small clip to give you an overview of Idea Statica, which goes beyond the anchor and steel to concrete connections. So let's watch this small.
Do you struggle with connection design? Meet Idea Statica Connection, the world's most powerful steel connection design and check software. Choose from thousands of ready-built connection design templates. Import your connections directly from your detailing software. You can also import models, including internal forces, load cases, and combinations from your analysis software. Or even start from scratch and model any connection matching your needs. So your project with a proper report, with all code check equations, bills of material, and sketches. You can also export the connection in IFC format and share it with your detailer. Visualize how your connection behaves and confirm your assumptions in just one click. Classify the connection stiffness as pinned, semi-rigid, or rigid. Find the real load capacity of connections. Perform seismic design. CBFEM, the calculation method powering our software, is co-developed with and verified by top universities from the US and Europe. You can be sure you're always working on the most powerful and proven software available. React to change requests quickly, see the updated results, and ensure buildability. Idea Statica Connection includes AISC, Eurocodes, Canadian standards, Australian standards, Chinese national, Indian, and Hong Kong standards, as well as all cross-section databases and units of measure, meaning you get the tools to handle any project anywhere. Download your free 14-day trial and calculate yesterday's estimates.
Perfect. So you saw in the video that how basically the Idea Statica helps in you to design the connections which are beyond the scope of PROFIS Engineering, and how that the two solutions can work together uh, to produce uh, value for you. So to conclude this webinar, um, I would like to point out the three main challenges that we talked about in the beginning of the webinar: the workflow integration, the rigidity check, the transparency regarding the full baseplate design with CBFEM. I can say the same thing. You have the single solution for all the three challenges to design the steel to concrete overall connection, and that's one solution is PROFIS Engineering. That's your ultimate solution to design the anchoring to concrete solutions along with the full base plate. And with it, I like to point it out to some of the resources for continuous learning. So if you are new to PROFIS Engineering, you can visit to profisengineering.hilti.com. There you can sign up and get the 30-day trial to the premium version of PROFIS Engineering. And here we are going to share this link with you so that in case you want to try it right now, please go ahead. We have Engineering Center where you can ask technical questions and learn key topics, watch the recording of the previous webinars, and you can visit using your local Hilti website and click on Engineering Center. On the third, which is super important for the topic which we were discussing, is the e-learnings. And this is something you can access from PROFIS Engineering itself. So if I show you this, at every PROFIS Engineering page, you will find these e-learnings courses at the bottom right of the page. And then once you click on it, basically it takes you to the steel to concrete course outline, and there you can find the advanced baseplate engineering training and the baseplate assumptions that you can learn from, and you can produce beautiful certificate of completion from Hilti site. So with this, we actually conclude this webinar series that had actually three chapters that talked about that how to do the structural data exchange, how to optimize your anchor system automatically, and then design your base plates, complete base plates with PROFIS Engineering. And with it, that brings us to the last poll of this webinar. And it's a very fairly simple question. Do you want us to connect you for implementing this solution in your workflow? And here comes your poll. So that's your poll. And let me give you a few more seconds to answer the poll question.